Welcome back, folks, to another exciting JLAM Bio video. My name is Joe Lamb, and I am excited to bring you the finale of our solutions unit. Yes, we are going to be focusing on colligative properties of solutions. So these are some unique properties that solutions have, particularly when we're looking at mixing a solute in a solvent. So we'll be looking at things like boiling point elevation, freezing point depression, as well as concepts directly related to what is known as vapor pressure. Super excited to bring this video to you today. Keep in mind this video is sponsored by Diet Cola. That's right, Diet Cola. All the taste and less calories. Oh, man. Let's get started. So hopefully by the end of this video, you will be able to explain a variety of colligative properties of solutions and to be able to calculate boiling point elevation and freezing point depression. Your key vocabulary terms here: boiling point, freezing point, vapor pressure, boiling point elevation, freezing point depression, and the Van 't Hoff factor. So let's talk a little bit about energy changes, and you should be very familiar with boiling point and freezing point. Simply put, the boiling point is the temperature at which liquid turns into a gas and gas to a liquid if you're going the opposite direction. The opposite, of course, would be condensation. Freezing point is which the temperature turns in a liquid to a solid or solid to a liquid, depending on whether you're melting or freezing. Now, this differs in different substances for a variety of reasons. This could differ due to the intermolecular forces that are present. This could differ due to whether the material is ionically bonded or covalently bonded. So lots of different ways to identify a melting point and boiling point, and just some examples of those here on the right. So keep in mind that when a substance goes through a phase change, energy is required to make that phase change happen without a change in temperature. So as you increase the amount of energy, and I know that you've seen this diagram on the right quite a few times before. So let's say you're in a solid, let's say you're ice, and you're increasing the temperature. Well, so let's say you're increasing the amount of energy into the system, the temperature tends to increase. Once you get to the phase change, though, notice that the energy input is a little bit different, or I should say the temperature is a little bit different, because as you input energy, the temperature actually stays the same. So energy is being utilized to go to transition in the phase change from a solid into a liquid. Now your question here is that are these endothermic or exothermic processes? And it's a difficult question to ask. You have to ask yourself, are you making or breaking bonds? Remember that endothermic processes break bonds and exothermic processes make them. So when you go from a solid to a liquid, you're breaking bonds. So transitioning from a solid to a liquid is actually an endothermic process. Energy has to go into the system in order to break those chemical bonds. If you go the opposite direction, going from a liquid to a solid, we're actually making bonds. We're tightening up those intermolecular forces. And as a result, that is an exothermic process because we are making chemical bonds. Now let's talk about vapor pressure for just a moment. I want you to think about a glass of water. The water actually evaporates even though it's not at the boiling point. So what's up with that? Why does that even happen? What's up with that? Jerry Seinfeld, don't worry about it. If this occurs in a sealed container, the gas will evaporate until the rate of evaporation is the same as the rate of condensation. So the liquid evaporates, and eventually the rate of evaporation and condensation actually happens simultaneously. The rates will be the same. This is known as dynamic equilibrium, and this is going to play a really important role in a lot of the stuff that we're going to be talking about in the future. Dynamic equilibrium doesn't mean that both substances are the same and then they just stay that way. It means that the rate of the phase change going one direction is the same rate of the phase change going the opposite direction. That's where the word dynamic comes in, because things aren't just static. They continue to move through this process. So when we talk about vapor pressure, keep in mind that when you put this in a sealed container, that the rate of evaporation is the same as the rate of condensation. It makes sense. That's why we capped our flasks in the previous lab. We capped them so that way the evaporated gas would not leave. It'll stay inside the container because the rate of evaporation is the same as the rate of condensation. So whatever evaporates eventually just condenses once again. The pressure that's exerted by the gas is actually known as vapor pressure. Now, the amount of pressure that is present is based off of a couple of different factors. This increases with temperature, which makes sense because as the temperature increases, it gets closer to the boiling point, which means that molecules are going to be more readily evaporating. Higher kinetic molecular energy or higher kinetic energy inside of the molecules means that they're moving faster, and therefore they're more likely to transition from a liquid to a gas. Lower intermolecular forces that are present result in a higher vapor pressure. That's one of the reasons actually why you tend to smell volatile organic compounds, is because they have relatively low intermolecular forces when compared to water. You really can't smell water. I guess you could smell moisture in a way. But you really can't smell it like you can smell something like gasoline, which has lower intermolecular forces. Lower intermolecular forces means that they more readily become a gas. And if they more readily become a gas, then it's going to exert more vapor pressure, because that is the pressure that's exerted by the gas itself. So do kind of keep these things in mind, that intermolecular forces and temperature play a role in how readily something becomes a gas, and therefore has a significant impact on the vapor pressure. So let's talk about some changes to boiling and freezing point. Boiling point and freezing point of substances are altered based on how much solute is dissolved in the solution. It also depends on the amount of solute that is put into the solution. The attraction of solvent particles to ions in solution is a key role in this. When you have solute in solution that forms ion-dipole bonds, and in many instances these ion-dipole bonds are stronger than that of the intermolecular forces that are present in between the liquid itself. So when we add a solute to it, this actually impacts the boiling point and freezing point. This causes the boiling point to increase and the freezing point to decrease. You see this when you took salt and put it in boiling water to cook your macaroni and cheese or to cook pasta. It actually increases the point in which the water boils. So instead of cooking at 100 degrees Celsius, you might be cooking at 102, 103, 104. Same thing when we add salt to roads in the middle of winter. The salt decreases the freezing point and therefore actually melts the ice at a lower temperature. So we can calculate this change in temperature by utilizing the formula delta TF equals Kf times small m times I, or delta TB equals Kb times m times I. And this is where Kb or Kf is the boiling point and freezing point constant, so those will be given to you. Little m is molality, which is moles of solute divided by kilograms of solvent, and I is the Van Hoff factor, which we'll talk about in just a moment. So Kb and Kf are determined by the solvent. So you want to look at what you're dissolving in, and that will help you determine Kb or Kf. Your molality is moles over kilograms of solvent, which again is fairly easy to calculate. Now I is the Van Hoff factor, which is determined by how many individual molecules dissolve in the solution. So for example, NaCl, you know by the dissociation equations that we've been talking about, breaks apart into two separate ions, one sodium and one chlorine. AlCl3, however, dissociates into four individual ions, one aluminum and three chlorine. That some nonpolar solvents do not dissociate. Okay? We won't get into the details of that here, but for example, if we were to use ethanol, ethanol would have a Van Hoff factor of 1. These are pretty easy to calculate once you kind of understand what's going on here, so let's do a couple practice problems and we'll be done. Determine the freezing point of an antifreeze solution when 4,000 grams of antifreeze is placed into 6 liters of water where the Kf is 1.86. Okay? So we are looking at freezing point here. So we know that our change in temperature is equal to Kf times molality times I. Well, my Kf is given 1.86. My I, we're going to figure out in just a moment. Oh, no, sorry. My I value here, if I take a look here, is there metal in here? It's not ionic, right? So the I value here is going to be 1. And then molality. So remember molality? Whoa. Moles of solute over kilograms of solvent. Okay. 6 liters of water. Well, we know that 1 gram is 1 milliliter. So if we have 6,000 milliliters, we have 6 kilograms. Moles. I got 4,000 grams of antifreeze. And we just need to convert that to moles. We got 62.08. We're going to convert that to moles. We get 63 0.69 moles of antifreeze. Okay. So we're going to plug that in here to get our molality. This is going to be 10.6 little m. So now I just plug everything into my formula. So we get delta T equals 1.86 times my molality, 10.6, times my I value, 1. We get 19.74. Now be careful here. This is the change in temperature. We're looking at water, right? And water freezes at 0 degrees Celsius, right? So I want to know the freezing point. So if my temperature is going to change 19.74, remember it's freezing point depression. So my final temperature is negative 19.74 degrees Celsius. Okay? And just make sure you RTFQ and follow the directions very, very closely. Let's do one more practice problem. Went ahead and opted not to do the last practice problem. I think you guys have a pretty good idea of what's going on here. Just make sure you remember that Von Hoff factor. And again, we'll practice this in class so you guys will have a really good idea of what's going on. Hopefully you have a pretty good idea of what you're doing. Make sure you're able to complete the learning objectives for today, and we will talk to you later. Have a great day, guys. Bye-bye.